Welcome back. Module 4 covers energy basics and fundamentals. In this lecture, we'll introduce the first and second laws of thermodynamics, including the different forms of energy and energy conversions. So let's get started. All right, we've gotten through the vocabulary, some background, some history on energy transitions. Let's talk about energy basics and fundamentals. Let's talk about the science of energy, the engineering of energy. And let's start with the first law of thermodynamics. This is one of the most important engineering principles that you can learn. We engineers have to learn Shakespeare. Everyone else should have to learn thermodynamics. This is engineers' Shakespeare. Thermodynamics drives the world in many ways. And the first law of thermodynamics says that energy is conserved. That says the best you can do is break even, that energy can be neither created nor destroyed. The total energy of an isolated system remains the same. And energy exists in many forms, and energy forms can be converted from one to another. So we have a fixed amount of energy, but we can move it around from one form to another. So it's both a constraint and a liberation. We are constraining how much energy we have, but we can change its form to meet our needs and for convenience. So this is a good news, bad news story of the first law of thermodynamics. Let's talk about the forms of energy. Energy exists in many forms. There's a mechanical form of energy, like gravitational potential. If I hold a ball up in the air and let go of the ball, it will fall because it has potential energy here. If the ball is moving, it has kinetic energy. There's energy in the motion. There's also thermal energy, energy in heat. There's electrical energy, radiant energy, chemical energy, and atomic energy. I'm going to walk through each of these one by one. Mechanical energy is that associated mostly with motion or potential for motion. The force in an object is its mass times its acceleration. And the units might be newtons or pounds, depending on what unit system you're using. The force is mass times acceleration. The work, or the force over a distance, is just the force of that mass times acceleration times the distance over which that work is done. And it has the same units as energy. So work and energy are sort of the same thing, sort of synonymous. Work has units of energy, and work can be energy, and it takes energy to do work, that kind of thing. There's also potential energy, which is that ball I was holding up. It has its mass and a gravitational potential and a height above the ground. That's its potential for motion. So potential energy is a form of mechanical energy because it's a form of prospective motion. It's motion that's about to happen. Then once it's moving, it has kinetic energy, and that's the mass of the object that's moving times its velocity squared divided by 2. So we go from the potential energy up high to the kinetic energy as it's moving. And these are all describing forms of mechanical energy. And there's another variant, which is the wind power, which is the density times the area times the velocity cubed, gives us the amount of power we get out of a wind turbine, for example. We're going to come to that again in the renewable energy lecture. So there's mechanical energy, different forms of motion, prospective motion or potential motion, as well as active motion, and the energy wrapped up in it. Thermal energy is essentially kinetic energy at the molecular level. As molecules bounce off each other, they exchange energy in collisions, and that causes things to heat up. And that heat is measured in terms of thermal energy. And the heat capacity is the ability of a particular material object to store energy. The heat capacity of air is different than the heat capacity of water, for example. That's thermal energy, heat, which is really just a form of kinetic energy, but at molecular level, we don't feel the molecules, we feel the aggregate effect is heat or higher temperature. Electrical energy is a particular form of energy that moves with electrons, and it's described in terms of its current in amps, its resistance of the device through which it's flowing in ohms, and its voltage, or the electric potential, in volts, and the power watts, or volt amperes, is related to each other. So the current I equals V over R, the resistance R equals V over I, the voltage V equals I times R. And there's a way to remember this, which is this diagram, V over IR. The way to remember that is vultures fly over Indians and rabbits. And the way you use this relationship is if you want to know what I is, you cover up the I equals V over R. If you want to know what R is, you cover up the R equals V over I. If you want to know what V is, you cover up the V, is equal to I times R across. So the math, the multiplication and division is shown in this diagram to show the relationships for these different forms or different factors that describe electrical energy. There's also radiant energy, which is energy that moves by waves. Things like light, electromagnetic radiation. Light waves carry energy. The sunlight can cause burns, sunburns. That's the energy in the sunlight being carried by radiation to your skin. There's also things like acoustic waves, which can destroy buildings or clean jewelry. A lot of the problem from bombs isn't the shrapnel, it's the acoustic wave that knocks buildings over. There's a lot of energy in radiant form. Then there's chemical energy. Energy is stored in the chemical bonds of molecules, and as those chemical bonds are broken, heat is released if you have a fuel molecule. So we have hydrocarbon chains, you break that chain and that bond, that chemical bond, energy comes out, heat comes out. The energy content in the chemical energy depends on the composition of the molecule, its masses and other properties. And this is a very important form of energy. It's responsible for more than 80% of energy in the US. This is the fossil fuels. This is the category that includes the fossil fuels like coal, oil, and natural gas. Chemical energy is very important. It is the energy bound up in the fuel that we then release into heat later on when we break those bonds through combustion. There's also atomic energy. Here, the energy is stored in the atomic bonds instead of the chemical bonds. And as those atomic bonds are broken, heat is released for particular types of molecules, for radioactive molecules. And this has an important effect here, which is the mass and energy equivalence, E equals mc squared. Well, c is the speed of light, 3 times 10 to the 10 centimeters per second. So when you square the speed of light, multiply that by mass, what it means is small changes in mass yield a lot of energy. And as you react the different radioactive molecules, the mass actually changes. You lose some mass. And let me give you just some background context for that. If you burn a ton of coal, a metric ton of coal, 1,000 kilograms of coal, 0.3 milligrams actually disappears. If you measure all the mass of the coal and all the oxygen coming in, then you measure all the mass of the reactants, 0.3 milligrams disappears, and that disappearance of mass became energy. Well, if you react a ton of uranium-235, a particular isotope of uranium, 6.6 grams disappears, which is 20,000 times more energy dense than coal. We're losing mass through these reactions, and that causes a translation into energy. And atomic energy has particularly good energy density because its atomic reactions release more mass or lose more mass than the chemical reactions. But the idea is basically the same, which is we're breaking bonds to release energy. We're breaking atomic bonds to release energy compared to chemical energy where you're breaking chemical bonds to release energy. Driving all these conversions are a series of gradients. Gradients are differences. Differences in temperature, pressure, height, electronic potential, salinity, altitude, chemical energy potential, that kind of thing. These gradients drive it. A temperature gradient is what we get from combustion. A temperature gradient is driven by high temperature gases in a combustion chamber, for example, pushing the pistons as they try to expand out to the cooler atmosphere. There are pressure gradients of flowing air that drive wind turbines, electronic gradients that drive solar PV output. There are salinity gradients where salt water meets fresh water that can drive different materials through membranes to give you power as well. Altitude gradients of falling water, or that falling ball we talked about earlier. And there's chemical energy gradients that help drive a lot of these combustion reactions. So these gradients, these differences are the key to the energy system. They drive the conversions from one form to another, and they are what determine the efficiency and the outcome of these different processes. There are different energy conversions to keep in mind. Too many to list here, but here's some samples. Things like thermomechanical, where we take heat to motion. Like in an engine, you have heat, thermal energy in high temperature gases that push the pistons to give you motion. You have thermochemical energy, where you take thermal energy to get chemistry or chemistry to get thermal energy. Things like combustion or refining or distillation, where you're changing chemical composition with heat or you're changing the chemical composition to get heat. There's also thermonuclear, where you use atomic energy to get heat. Electrochemical, where you get chemical reactions straight to electricity, like, for example, in a fuel cell or in a battery. You have electromechanical, where you have generators, electric motors, where you go from motion to electricity or electricity to motion. Then you have things like photoelectric, photovoltaic, optoelectronic, where you go from light to electricity or from electricity to light. And then you also have photochemical, things like candles, where you go from chemical energy in the wax or the paraffin to light or radiant energy. All these different conversions that drive what we want, and we can manipulate them to achieve a particular outcome. We can start with a fuel we need or want, and then push it through some conversions and gradients to get the outcome we desire, the end use we need. Maybe we want light, maybe we want heat. Now, all of these conversions have a downside, which is they have losses associated with them. And those losses are determined by the second law of thermodynamics, another important fundamental law. The first law of thermodynamics says energy is conserved. The best you can do is break even. The second law of thermodynamics says that entropy or disorder increases, which is you can't even break even. You're going to have losses along the way. And entropy manifests itself this way in the form of inefficiencies. No system gives you as much back out as you put in. Losses always occur. Systems move from low entropy or high order to high entropy or low order. And let me give you an example of what that means. It means, globally, declining resources. But the reason is because we go from highly ordered forms of energy, like a lump of coal. That's highly ordered because in my hand, I have a lot of energy that's highly ordered. But as I burn it, it disperses as smoke and heat around the room, becomes highly disordered. That's a statement about entropy. That's a statement about the second law of thermodynamics. It's easy to go from fuel to heat. It's really hard to go from heat to fuel. I could burn a lump of coal and fill this room with smoke, but it's really hard to take that smoke and make fuel. So the second law of thermodynamics gives us a direction in our processes or our conversions, and it gives us losses. And it's hard to reverse those losses. And what this means globally is that thermodynamics has determined that our resources will decline. We can go from reserves of oil and gas and coal to heat and end uses, but it's really hard to go the other way around. In fact, the main conclusion is that the availability of useful forms of energy can only decline. However, The Earth isn't closed to solar radiation. This is for a closed system. Closed systems, the energy must decline. But in an open system, you can keep having energy. So the Earth is actually open to solar radiation, and the Earth is open to the moon's gravitational forces. So those are not determined to decline in the same time scale as the resources within the Earth. So this is the challenge. The first law says we can convert from one form to another. The second law says as we do those conversions, we'll have losses, and we will deplete the fuels. We can measure these efficiencies in a variety of ways. Generally, the efficiency is what you get out over what you put in, and there's some losses. The efficiency is always less than 100%. Well, for a heat engine, for anything that uses heat to make motion or heat to do something else that's useful, and that's most things, we can measure the total ideal efficiency with what's called the Carnot efficiency, which is the best possible efficiency you might achieve from a heat engine. And because heat flows from hot to cool, we could use those temperature differences to make work. The way we assess the ideal efficiency, the Carnot efficiency, equals 1 minus the ratio of cold over hot temperatures. Those are absolute temperatures in Rankine or Kelvin, not Celsius or Fahrenheit. So we can think about the temperature inside an engine versus the temperature outside. The temperature outside is a cold temperature. The temperature in the engine is a hot temperature. And those ratios, the inverse of the ratio, subtracted from 1, gives us the ideal efficiency for that engine. And the unfortunate thing is all engines have losses. Even an ideal engine will have losses. And these engines include things like power plants, internal combustion engines, jet engines, that kind of thing. All these conversions we're going through, they have losses. And at best, they can do according to the Carnot efficiency. We can go through examples online of different ways to calculate the efficiency using different conditions. Now, those efficiency losses work against you. Efficiency for a process is always less than 1. And for a system, or for a series of conversions, the overall efficiency is the product of the individual efficiencies of each step. It's not the sum of the efficiencies. It's not the average of the efficiencies. It's the product. So if you have 5 conversions in a row, you have to multiply 5 efficiencies in a row to get the total efficiency. Minimizing the number of steps or minimizing the number of conversions is therefore beneficial. And usually, we need these multiple energy conversions. So this is the challenge. Let me give this example here. We want to light up a light bulb using coal-fired electricity. Well, this process goes through 4 conversions and 5 forms of energy. We begin with chemical energy, the coal, and we end with radiant energy, the light. And the overall process is from chemical to radiant energy. But we actually go from chemical to thermal to mechanical to electrical to radiant energy. The first conversion is chemical to thermal. We burn the coal in a boiler to generate heat. That heat in the form of steam then drives a steam turbine, which is the second conversion. We go from thermal energy to mechanical energy. The third conversion is that mechanical energy to electrical energy as that motion spins a generator, which gives us electricity out. And then the fourth conversion is the light bulb, as the electricity goes through the light bulb to convert electricity to light. 5 forms of energy, 4 conversions. Each conversion has a loss. And if we look at those losses, they end up being pretty severe. We have fuel and air coming into the boiler that's burned, giving us heat, thermal energy. That thermal energy makes steam that carries the thermal energy to the turbine, the steam turbine. That thermal energy expands through the turbine to give us motion. That motion drives the generator to give us electricity. That electricity then can go on to the light bulb. If we look at just the power plant, the boiler has an efficiency of something like 90 to 98%. And that's a conversion from chemical to thermal energy. The large steam turbine has an efficiency of 40 to 45%. And that takes us from thermal energy, steam, to motion, spinning turbine blades. And the electricity generator has an efficiency of something like 98 to 99%, which is really efficient. And that takes us from motion, spinning magnets, to electricity. Well, the total efficiency for the system is the product of those 3 efficiencies. The efficiency of the boiler times the efficiency of the steam turbine times the efficiency of the generator. And in total, that means your efficiency is like 35 to 44%. This is the typical efficiency of a U.S. power plant. In fact, most power plants are even lower, like 30 to 35%. It's because each conversion has a loss. It's because of the second law of thermodynamics. And those losses stack up so that they're multiplied, in total giving you something much lower than the individual efficiency of any particular component. Well, if we expand that system to include transmission and the losses with transmission, it gets even worse. You have the power plant is like a 35% efficiency at the start of this chain of events. Then you have transmission as about a 90% efficiency. Maybe it's really 93%. Then you have a light bulb with 5% efficiency. And if you go through all that and multiply them out, you get 35% efficiency times 90% efficiency times 5% efficiency. You get a net end-to-end efficiency of 1.6%. For every 100 units of coal energy, you get 1.6 units of light energy out of the light bulb. That's the bad news of the second law of thermodynamics. So we're having losses along the way. Reducing the losses, making every device more efficient is a step. Using something other than light bulbs might be another way to go, or more efficient light bulbs, using windows and natural lighting. We can see that losses are severe as they incur through the system. And one of the lessons we'll come back to in the discussion of the electricity sector is that the electricity system is wasteful actually the whole energy system is wasteful, but let's just use electricity as an example right now. We start off with 40 quads of energy consumed to make electricity. We lose 26 quads at the power plants from the losses for the reasons we just discussed. We lose another quad of energy in the transmission lines across the nation. And we end up with about 13 quads of useful electricity at the end. The energy system is wasteful. We lose a lot of heat along the way. We lose a lot of energy. And that's because of the laws of thermodynamics. It's hard to escape. And so we have to use good design and good engineering whenever we can to improve the efficiencies. We have to use good decisions to avoid the energy consumption wherever possible, because every unit of energy we consume has other energy consumed elsewhere in the supply chain. This module had a lot of details and a lot of data. So to get some reinforcement, go online, do the exercises, and then I'll see you at the next lecture.